Hello everyone. In this video, we'll go through question number 21 to question number 30 from the chapter Making Measurements. Now let's take a look at question number 21. The diagram shows pendulum. The pendulum bob swings repeatedly between points M and N. A student starts a stopwatch when the bob starts point M. He counts each time the bob changes the direction and stops the watch on the 10th change in the direction. The watch shows a time of 12.0 seconds. What is the time period of the pendulum? Now let's try to understand how the measurements are being taken. So every time the bob changes the direction, the student starts counting. So let's say if it goes back and forth, it will be counted as 1 and 2. So if the person counts twice, then it is one complete oscillation. Now let's check how many times he counted the bob. The change in directions, there were 10 change in directions. So if there are 10 changes in directions, that means there were 5 oscillations. Now the time taken for 5 oscillation is 12 seconds. We have to calculate what is the time taken for one oscillation. So the time taken for one oscillation will be 12 divided by 5. So let's take out our calculators and let's measure what is 12 divided by 5. So let's say 12 upon 5 would give us 2.4. So the answer will be 2.4 seconds. So that's the time period of the pendulum. Let's look at question 22. A student measures the volume of 3 liquids using 3 different measuring cylinders. The table shows the volume recorded by the student. Which reading are correctly recorded? Now let's take a look at all the readings of these measuring cylinders. Let's look for the first cylinder. So it is 0.51. So it is we should always look at the lower meniscus. So this is 1.1 and this reading here would be 1.2. So let's write that down. This is 1.2 cm cube. Here again the graduations are 0.2 cm cube. So if this is 2, then this reading will be taken as 2.2 cm cube, 2.4 cm cube, 2.6 cm cube and so on. So the measurement here will be 2.4 cm cube. For the third one, again the graduation is 2 cm cube. So here the graduations are 2 cm cube. So from here this will be read as 20 cm cube, 22 cm cube, 24 cm cube, 26 cm cube and so on. While measuring for this measuring cylinder, let's look at the lower meniscus. The lower meniscus is between 24 and 26. So we can consider this to be 25 cm cube. Now let's look at the table. The first measuring cylinder, the measurement was taken as 1.2 cm cube, that is correct. For the second one, instead of taking it as 2.4, the student has made a mistake by calling it as 2.2, so this is incorrect. For the third one, the volume is 25 cm cube, so this is also correct. Now out of these three things, only 1 and 3 are correct, so let's mark option C, 1 and 3 only. Let's take a look at the next question. A student uses a meter rule to measure the length of a sheet of paper. Which measurement is shown to the nearest millimeter? Okay, so we have different options. So if I take 1 meter, right, let's say if I take this as 1 meter, 1/10 of a meter is called as a decimeter. Then 1/100th of a meter is called as a centimeter, and 1,000th of a meter is called a millimeter. Now, if I want to check to the nearest millimeter, then I should have a 1,000th place in my value. Here, let's look at this. So 0.3 meter is 3 decimeter. So this is not correct. So 0.29 meter is 29 centimeters. So this is also not correct. Let's look at this. 0.293 meter. So 0.293 meter is 293 millimeters. So this option is correct. So the correct answer is option C. Let's look at question 24. For which one of the following measurements would a micrometer screw gauge be most suitable? So a micrometer screw gauge is used to measure distances or lengths which are in the scale of millimeters. So if I take the length of the page, it is in centimeters, so we might not be using micrometer screw gauge. Length of a pencil, we can still use a meter scale to measure this. Diameter of a wire, yes. To measure the diameter of a wire, we will be using a micrometer screw gauge. Diameter of an atom is so small that we can't use a micrometer screw gauge. It is very smaller compared to the dimensions which can be measured by the micrometer screw gauge. So only diameter of a wire can be measured. Let's look at question 5. The diagram shows a measuring device. For which measurement is this device suitable? So the device which is shown to us is a micrometer screw gauge. There are different parts of a micrometer screw gauge. Let's just get a quick overview of what a micrometer screw gauge is and how it will work. So let's look at this. So this part of the micrometer screw gauge is called as anvil, and the moving part here is called a spindle. The U-shaped part here is called as a U frame, and what we see here is main scale and this is the circular scale. Then the entire body, this body of the micrometer screw gauge is called thimble, and the last part here, the rotating part, is called a ratchet speeder. Now, as you can see from the main scale is in millimeters, which means we can measure things which are of the size, which have the size of millimeter using a micrometer screw gauge. So millimeter, and the smallest value it can measure is 0.01 millimeters. This is also called as the least count. Now let's look at the options what we have. So we have diameter of a cylinder of aluminum about 20 centimeter. So we won't be using this. We'll be using a different instrument called vernier caliper. Then we have distance between two molecules of zinc. So this distance is very small, so this can't be measured with micrometer screw gauge. Then length of a rod of iron about 1 meter, this is also very small. Then thickness of a sheet of copper of about 1.5 millimeter. So this we can measure it using micrometer screw gauge. Now we'll have a deeper understanding of how a micrometer screw gauge works. So we'll quickly take a look at how a micrometer screw gauge works. Alright, so we have a micrometer screw gauge with us. As I said, we have different parts of a micrometer screw gauge. This is the anvil, this is the spindle, this is the U frame. Then we have the main scale, we have the circular scale, we have the thimble, and if I just minimize this window, we can also see the ratchet. Now, so if I spin this ratchet speeder, right, the micrometer screw gauge closes up. We can also use it to open up the micrometer screw gauge. So let's say once I close this cap, I can hear a small click from the instrument. So even in lab, when you go there, you can also use micrometer screw gauge, and you will always hear a small click once it is completely closed. Let's wait for that click. Alright. Now let's look at the reading here. On the main scale, it is read as 0. On the circular scale, it is also read as 0. That means we have a perfect micrometer screw gauge with us. If I want to measure the thickness of this small piece of metal, I can place this between the anvil and the spindle. Then let's close the gap. Before closing the gap, let's also look at what the main scale reading is. So here in main scale, every graduation is 0.50 millimeter. So this is 0.50 millimeter, this is 1.00 millimeter, 1.50 millimeter, 2.00 millimeter, again 2.50 millimeter, 3.00 millimeter, and so on. And in our circular scale, we have the circular scale goes from 0 to 50. So it goes from 0 to 50, which means I can measure something like 0.01 millimeter to 0.49 millimeter. So let's quickly keep this. Then let's close this spindle and let's wait for the click. Alright, now it is completely closed. Let's take the reading. So it is 0.50, 1.00, 1.50 and 2.00. So it is 2 millimeter on the main scale. On the circular scale, we are reading it as 25, which means this is 0.25 millimeter on the circular scale. Once we add both of them up, that means 2.00 plus 0.25 millimeter, that will give us 2.25 millimeter, which is the actual thickness of this piece of metal. So on the main scale, we are reading 2.00 millimeter. On the circular scale, we are reading 0.25 millimeter. So that's 25 circular scale divisions. So the actual thickness of this piece of metal is 2.25 millimeter. So this is the reading for an ideal case. But our micrometer screw gauge can have errors. For example, let's say I've closed this entire thing up and I'm waiting for both the zeros to match up. So now both the zeros are coinciding. That means there are no errors in our main scale as well as our circular scale. But in some cases, as you see in laboratory, right, there will be small additional values which you see. Even though when the circular scale is completely closed and we hear a click, the scales do not match up. That means there is an error of 4 units on our circular scale. So this is called as zero error. Zero error is a systematic error, and this is from the device itself. This error exists in the device. Let's place the same object back and try to read what the measurement is. So when I place this object back, on my main scale I am reading 0.50, 1.00, 1.50 and 2.00. So this is 2.00 millimeter plus, instead of overlapping at 2.5, now it is overlapping at 2.6, 2.7, 2.8 and 2.9. That means 0.29 millimeter is on the circular scale. So 2 plus 0.29 will give us 2.29 millimeters. So our the micrometer screw gauge reading now is 2.29 millimeters, which is 4 more compared to what is the actual thickness of this piece. So every time we measure something, first we have to look for the zero error, and because this zero error is already added up when it was completely closed, right, our micrometer screw gauge was already reading 4. So let's subtract that value from the reading what we measured. So 2.29 minus 0.04 millimeter, and that would give us 2.25 millimeter, which is the actual thickness of the metal. So the zero error right now here is positive, but that might not be the case all the time. The zero error can even be negative. So if I go back like this, so here as you can see, our main scale was here. I was going to the right of main scale, so the zero error was being positive. So if I get that I am going to the left of main scale, that means the zero error here is negative. So let's say I have a zero error of -3. So instead of showing 0 coinciding, now when I read it, it is actually showing 47 on the circular scale division. That means I have moved back by 3 units. When I place my piece back, so let's read what this reading says. It is 2.00 millimeter plus 22 readings on the circular scale division. That means 0.22 millimeter here. So 2.00 plus 0.22 is 2.22 millimeter. So if I add up the zero error, so if I add 0.03, so that will give us 2.25 millimeter, which is the actual micrometer screw gauge reading. So I hope this clears up any doubt regarding micrometer screw gauge. We'll go back and solve a few more questions. Alright, let's take a look at the next question. A micrometer screw gauge reads 0.02 millimeter when the jaws are fully closed. It reads 0.56 millimeter when measuring the diameter of a metal wire. What is the diameter of the metal wire? So this 0.02 millimeter is the zero error. Now when we read 0.56 millimeter, it has already included this 0.02 millimeter along with it. That means we have read 0.02 millimeter more compared to what should have been the actual value. So let's subtract that 0.02 from the measured value. So 0.56 millimeter, this was the measured value, minus 0.02 millimeter, this is the zero error, and here zero error is positive. So this will give us 0.54 millimeter, and that will be the actual diameter of the wire. So this is the actual reading or actual value. So the correct answer is option B. Let's look at question 27. A pendulum makes 50 complete swings in 2 minutes 40 seconds. What is the time period for one complete swing? So for 50 swings, it takes 2 minutes 40 seconds. Let's convert this into seconds. So 2 minutes 40 seconds is 120 seconds plus 40 seconds, and that would be 160 seconds. So for 50 swings, it takes 150 seconds. For one swing, right, what is the time taken? That's the time period of the pendulum. So it will be 160 upon 50. Let's take out our calculators and start inputting these values. So 160 upon 50 is 3.2. So this will be equal to 3.2 seconds. That's the time period of the pendulum. So correct answer is option B. Let's take a look at question 28. 5 athletes P, Q, R, S and T compete in a race. The table shows the finishing times for the athletes. Which statement is correct? Now, we have 4 options. In 2 of the options, they are saying athlete P1 and the other 2 they are saying athlete S1. First, let's check what's the time of athlete P and athlete S. So, athlete P finishes the race with a time of 22.50 seconds. Athlete S finishes the race with a time of 26.50 seconds. That means athlete P is faster than athlete S. So this is position 1. So athlete P won the race. That means we can directly eliminate 2 options. Let's look at which among these 2 are correct. So athlete P won the race and was 0.70 seconds ahead of the second place. Ahead of athlete in the second place. Then it says athlete P won the race and was 1.90 seconds ahead of the athlete in the second place. Now we have to check who was in the first place, who was in the second place and so on. So athlete P was in the first place. Let's look at the next fastest timing. The next fastest timing was from athlete T. So here this will be position 2. Then this is position 3. Here is position 4 and this is position 5. Now we have to check how fast did athlete P win the race compared to athlete T. So let's just subtract the 2 values. We have to subtract 23.20 minus 22.50. This will tell us the gap between them. Let's open up the calculator. (23.20) minus 22.50, that is 0.7 seconds. So athlete P was 0.7 seconds faster compared to the athlete who was in the second place. So option A is correct. Option B will be deliberately given to misguide you, because you might think, okay, if this is position 1, this might be position 2, this might be position 3, and if you actually calculate the difference between P and Q, it would come around 1.9 seconds. So these kind of options will be deliberately given to misguide you, but what you have to do is you have to make sure who are in the first place, who are in the second place, and let's put up this hierarchy table, and then we can calculate the gap between them. Okay, let's look at question 29. Diagram 1 shows a solid rectangular sided block. The diagram 2 shows the same block from the front and from the side. Meter rules have been shown close to the edges of the block. What is the volume of the block? We have a cuboid with us, so the volume will be equal to length times breadth times height. First, let's figure out what's the length. So here in our diagram, let's say this is the length, this is the breadth, and let's say this is the height. Now from the front view, we can actually calculate what is the length and what is the height of this cuboid. If I take this as the length and this as the height, then the length of this will be 11 minus 4. So 11 minus 4 is 7 centimeter. So 7 centimeter is the length of this block. For the height, we have to subtract 5 and 1. So 5 centimeter minus 1 centimeter. So that's 4 centimeter. That will be the height of the block. Now if I want to calculate breadth, let's look at the side view of this. So 21 minus 15, and that is 6 centimeter. So 6 centimeter will be the breadth of this block. Let's input all these values in the formula. So this will be equal to 7 times 6 times 4. Let's use a calculator to compute this. Seven times 6 times 4 is 168. 168 cm cube will be the volume of this cuboid. So the correct answer is option B. Let's look at question number 30. The diagram shows a rectangular metal sheet close to two rulers. What is the area of the metal sheet? First, let's find out what is the length and what is the breadth. So the length of it, so here it is 25 centimeter on this ruler. Here, let's say this is 5 centimeter here. So 25 minus 5, that will be 20 centimeter. So if I call this as length, this as breadth, the length is 20 centimeter. To calculate breadth, let's find out what are these readings. So it is 45 here and 10 over here. So the breadth will be 45 minus 10, that is 35 centimeters. To find the area, we can use the formula area will be equal to length times breadth, because this is a rectangle. So this will be equal to 20 times 35. Again, use your calculators to calculate this. So 20 times 35 is 700. So the area is 700 centimeter square. This will be equal to 700 centimeters square. So the correct answer is option A.